We will now look at some applications of exponential functions. We'll talk about these more in depth in later sections, but we will start exploring how exponential functions can be used to model quantities that grow or decline very rapidly, such as the population of a country, the growth of bacteria, the amount of a chemical element, or the amount of money in an account. So how do exponential functions actually model growth? So I want to look at two functions, f of x equals 2 to the x, and f of x equals 5 to the x. And let's just look at their output values for x values of 0 and larger. So I have a chart for each of these functions where the x values are 0, 1, 2, 3, and 4. And then we have a column for the corresponding y value. So let's focus on 2 to the x right now. We've already looked at this before, right? 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, 2 cubed is 8, and 2 to the 4 is 16. So when we look at these values and think about the slope between consecutive points in our table, if I find the slope between the points 0, 1 and 1, 2, the change in y over change in x is 2 minus 1 divided by 1 minus 0, which is 1. When I do that for the ordered pairs 1, 2, and 2, 4, I get that the slope is 4 minus 2 divided by 2 minus 1, which simplifies to be 2 over 1, or 2. And then for the slope between 2, 4, and 3, 8, the slope is 8 minus 4 divided by 3 minus 2, which is 4 over 1, or 4. And lastly, between 3, 8, and 4, 16, the slope of the line between those 2 points would be 16 minus 8 divided by 4 minus 3, which is 8 over 1, or 8. And so when I talk about the slope in this context, this is really the slope of the secant line between these two pair of points. And notice that the slope is not constant. In fact, that is how we know we have a linear function. If the slope between any two pair of points in the line is the same, then we have a linear function. I don't have a linear function because the slope between these consecutive pairs of points is not the same. But notice what is happening. The slope goes from 1 to 4 and 8. And if you remember, as the slope increases, that means that the line between those 2 points gets steeper and steeper and steeper. So if we're thinking about a secant line between these 2 points, we're getting more and more vertical, which is really showing that between consecutive pair of points, we're getting an increase in the output values, right? The y values are growing very quickly. The other thing I want us to note is how these y values relate. So we see that there's not a constant slope. The slope is actually increasing through those pairs of points. But what happens if I find the quotient of the y values? And so if I look at 2 divided by 1 is 2. Then 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. So for an exponential function, what we find is that the ratio of the y values is actually constant. And that should be a little bit evident, right? Because when we say 2 to the x, we're really talking about x copies of 2, right? So 2 to the 1 is just 2. 2 squared is 2 times 2. So we have a constant multiplier as we increase our input value. Another example of f of x equals 5 to the x. So 5 to the 0 is 1. 5 to the 1 is 5. 5 squared is 25. 5 cubed is 125. And 5 to the 4 is 625. In a similar fashion, we can look at the slope between consecutive pairs of points. between 0, 1, and 1, 5, we get 5 minus 1 divided by 1 minus 0 is 4. 25 minus 5 divided by 2 minus 1 would be 20 over 1, or 20. And then between 225 and 3, 125, those two order pairs, the slope would be 125 minus 25 divided by 3 minus 2, which is 100. The last pair of points, 3, 125 and 4, 625. Our slope is 625 minus 125 divided by 4 minus 3, or 500. So again, we see that there's not a constant slope. The slope is actually increasing. So that is, between the 2 points, we're actually getting steeper and steeper and steeper. And if we look at the quotient of consecutive y values, 5 divided by 1 is 5. 25 divided by 5 is 5. 125 divided by 25 is 5. And 625 divided by 125 is 5. So again, there's a constant multiplier as we go to the next x value. I'll go back now to think about what we were talking about, but I just wanted you to think about how those y values of an exponential function are actually relating to one another. So there are two types of interest that we're going to focus on. Really only one of them, but I'm just going to tell you there's two types that banking typically uses, and that's a simple interest and compound interest. And simple interest is interest calculated on only the amount invested or the amount borrowed. Simple interest is computed using the formula I equals P times RT, where I is the interest, P is the principal amount, that is the amount you initially borrow or the amount you initially invest. R is the interest rate, we always convert to a decimal, and T is the time in years of investment. This is not the main formula we're going to look at, but this is the one that drives the next formula that we're going to talk about. And if you look at the text, you can see an explanation of where this compound interest formula comes from that we're going to talk about. Compound interest is interest calculated on the amount invested and the interest earned. And so that is, you might have a bank account that has $500 and you earned $1 in interest. Well, the next time they calculate the interest, it's going to be on the initial amount of $500 plus that $1 interest that you already earned, so the 501. So now you're earning interest on interest, which is really what compound interest is. So the compound interest formula states that the total amount A in an account after T years, if P dollars is invested at an annual interest rate R, compounded N times a year, is A, which equals P, times the quantity 1 plus R divided by N, all raised to the NT. Now, compounding is a number of times that the bank calculates interest on this account. So we can have a compounded annually, that means that interest is calculated one time, so we would say N is equal to 1. Compounded quarterly, that's every 3 months, so N would be 4. We can have compounded monthly. N would be 12. Have compounded daily. N would be 365. The expression R divided by N represents what interest are you earning at each period. Right, so that's really the interest rate per period, per time that you're calculating the interest. And N times T is going to be the total number of times that interest is calculated over the life of that investment. So let's just work with the formula, and it will be given to you on a test, but I think it's good practice to actually learn it and memorize it. It won't hurt you, but I know that sometimes that can be hard to do when you're first learning something. But in this example, we want to compute the amount in an account after 12 years if $4,000 is invested at an annual interest rate of 5% compounded. Then we want to look at annually, quarterly, or monthly. So let me add that this formula is assuming that you put the money in the account and you just let it build interest. You're not taking any withdrawals from the account. The money is just growing simply by the interest, earning interest on itself. So the amount in the account, we're going to use our compound interest formula, which is A equals P times 1 plus R divided by N raised to the N times T. So in this case, we're trying to solve for A. P is our initial investment, so that would be our $4,000, times 1 plus R is the annual interest rate, but as a decimal, so 5% would be 0.05, divided by N. We're compounding annually, so that would just be 1, since it's 1 time a year, raised to the N again, which is 1, times our number of years, which is 12. So we can input that expression on the calculator, and when we do that, 4,000 times 1 plus 0.05 divided by 1 raised to the 12 times 1, we're going to round to 2 decimal places since we're talking about money. The amount would be $7,183.43 since we're rounding to the nearest 2 decimal places. If we wanted to compound quarterly, the only difference in this calculation, we still have A is equal to P times 1 plus R divided by N raised to the NT. A would be equal to 4,000 times 1 plus our rate, which is 0.05, divided by N. So compounding quarterly means 4 times a year. And then we're raising that to 4 times 12. And again, on the calculator, we can compute what that would be. So 4,000 times 1 plus 0.05 divided by 4 raised to the 12 times 4. Our amount in the account would be $7,261.42. And then to compound monthly, the only change, still using this compound interest formula, but in the formula we would have 4,000 times 1 plus rate 0.05. Compounding monthly would be dividing by 12 and then raised to the 12 times 12. And so again on the calculator we can input that value to get that our ending amount would be $7,279.40. Now, some questions that you might ask is how much interest did you earn on that account in the 12 years? So if you subtract off your initial investment of $4,000, you're left with how much interest you earned in that time. So we have, in this first account, the interest that we actually earned by take off 4,000 would be $3183.43. Right, for the second one, the interest would be, subtracting off 4,000, 3261.42. And for the one compounded monthly, the interest earned would be 3279.40. So let me talk about another type of interest, and that is continuous compound interest. In the previous discussion, we were looking at increasing the number of times interest is computed each year, right? We went from annually to quarterly to monthly. And you might think that as you continue to increase the number of times interest is computed, that the amount continues to grow. But that's not true. There's actually a limit on the amount in an account. And the limit on the amount in an account is approximated by a continuous compound interest formula. So I have this illustration below. It is as n increases, the amount in the account approaches this expression involving the number e. But let me kind of explain what I have on the screen. So let's assume that we have $3,000 that we're investing at 4% annual interest for 10 years. And so just by the compound interest formula, we know that A, the amount in the account, would be our principal, 3,000, times 1 plus R, which is 0.04, divided by the number of compoundings, which we are not specifying right now, so we'll say n. And that's going to be raised to the n times t, so 10 times n, or 10n. So what we're looking at is what happens as n grows, like from 1, 4, 12, might be daily, right, 365, it might be every minute, every second. What happens as we earn interest that frequently? Well, what happens is that it actually approaches this number, 3,000 times e to the 0.04 times 10. And that is because, you remember I mentioned this briefly, but that the number e is actually from the limit as n goes to infinity of 1 plus 1 over n to the n. And so that's where we see this e, because of this fraction, 1 plus 1 over n to the n. And I explained this more in the book too. We're not going to really get into that at this moment, but what you really need to know is that there's a limit, and it approaches this number that involves e. And this is leading to the continuous compound interest formula that states that the amount A in an account, if P dollars is invested at an annual interest rate R, compounded continuously for T years, is A equals P times E to the RT. So if we want to determine the amount in an account, if $500,000 is invested at an annual interest rate of 4.7% compounded continuously for 5 years, we're going to see, oh, compounded continuously means we're going to use that continuous compound interest formula, which is A equals P times E to the RT. And so our ending amount is going to be 500,000 times e to the r, which is as a decimal 0.047, times the number of years, which is 5. And then we can use our calculator to figure out what that number is. When we enter 500,000, then you need to do the second ln to get this e to some exponent. And then 0.047 times 5 in the exponent, and we would get 632,452.38. So in the 5 years, we earned $132,400 plus dollars in interest. Now, here's another example that deals with exponential functions. It is modeling population growth. So we said that the population of India in billions can be approximated by the function f of x equals 1.282 times 1.0118 to the x, where x is the number of years after 2016. What is the population of India in the year 2016? And then we want to estimate the population in the year 2025. So the population of India in the year 2016, well, 2016 is 0 years after itself, so we would want to find f of 0, which is 1.282 times 1.0118 to the 0. But remember, A base other than 0 to the 0 is 1, so this is really 1.282 times 1, which is 1.282 billion. So the population of India in the year 2016 was 1.282 billion. Now to find the population in the year 2025, well, we need to figure out how many years after 2016 is 2025, and then we'll substitute that number into the function. And so I've done this calculation already on the calculator. 2025 minus 2016 is 9, right? So 9 years. So when we find f of 9, it's going to be 1.282 times 1.0118 to the 9. And entering that on the calculator, we get approximately 1.42 billion would be the population of India in the year 2025. So note that the base of this exponential function is a positive number greater than 1, which means that it does model exponential growth. That is, it's an increasing function. This multiplier is really a stretch factor, but what it really does is gives us the initial value of that function. And we found that when we substituted in 0, we got the 1.282.